Welcome to our deep dive into the fascinating question, is time travel possible? Today we will explore the science, theories, and popular culture that surround this intriguing concept. Get ready to embark on a journey through time as we unravel the mysteries of time travel. Time travel has been a staple in science fiction for decades, captivating our imaginations with the possibilities of moving through different points in time. From H.G. Wells's The Time Machine to the Back to the Future trilogy, the idea of traveling through time has sparked endless curiosity and speculation. But beyond the realms of fiction, is there any scientific basis for time travel? Can the laws of physics allow us to journey to the past or the future? In this video, we'll explore the groundbreaking theories and research that scientists have proposed over the years. Our exploration begins with the theory of relativity, proposed by Albert Einstein in the early 20th century. This theory fundamentally changed our understanding of time and space, suggesting that time is not a constant, but can be affected by speed and gravity. Could this be the key to unlocking time travel? Next, we'll delve into the concept of wormholes, hypothetical passages through space-time that could create shortcuts for long journeys across the universe. Some scientists believe that if we could harness these wormholes, we might be able to travel between different points in time. We'll also discuss the idea of cosmic strings, narrow tubes of energy stretched across the universe that could potentially allow for time travel. These strings, theorized to be remnants of the early universe, might provide the necessary conditions for moving through time. Quantum mechanics, the branch of physics dealing with the very small, also offers intriguing possibilities for time travel. Concepts like quantum entanglement and superposition suggest that the universe may be more interconnected than we realize, raising questions about the nature of time itself. Of course, time travel isn't without its challenges and paradoxes. We'll explore famous conundrums like the grandfather paradox, which questions the implications of changing the past, and the bootstrap paradox, which involves objects or information with no clear origin. As we journey through these scientific theories, we'll also take a look at how time travel has been portrayed in popular culture. From movies and TV shows to books and video games, we'll see how these fictional representations have shaped our understanding and expectations of time travel. Finally, we'll consider the future prospects of time travel. What are the latest developments in scientific research? How close are we to turning the science fiction of time travel into science fact? Join us as we explore these questions and more. Ancient civilizations were fascinated by the concept of time travel, often embedding it within their myths and legends. These stories reflect humanity's enduring curiosity about the past and future, long before modern science. In Hindu mythology, there are tales of gods and heroes who transcend time, such as King Raivata Kakudmi, who travels to meet the creator god Brahma, and returns to find many ages have passed. These myths reveal a belief in the fluidity and malleability of time. Greek mythology also touches on time manipulation, with the story of Cronus, the god of time. Cronus could control time, and is often depicted with a sickle, symbolizing his power to cut and alter the flow of time itself. Norse legends speak of Yggdrasil, the world tree, which connects different realms and times. This immense tree serves as a conduit through which gods and beings travel, illustrating a mythic understanding of time's interconnected nature. In Chinese folklore, the tale of the red thread of fate suggests a predestined connection between people that transcends time and space. This concept hints at an ancient belief in a timeline shaped by destiny. The Aboriginal Dreamtime stories from Australia describe a time when ancestral spirits created the world, a period that exists outside of conventional time. These narratives present a timeless dimension where past, present, and future are intertwined. Ancient Egyptian myths include the god Thoth, who is said to have the power to travel through time. Thoth's knowledge of time and magic illustrates the Egyptians' complex understanding of temporal dynamics. In Celtic mythology, the otherworld is a place where time flows differently, allowing heroes to return after what seems like days to find years have passed in the mortal world. These stories reflect a belief in alternate realms with unique temporal properties. The Mayans had an intricate calendar system that reflected their advanced understanding of time cycles. Their legends often involved gods and ancestors traveling through these cycles, influencing both past and future events. Persian mythology features the story of Jamshid, a king who possessed a cup through which he could see all the world's events, past and future. This suggests a form of time viewing or travel enabled by divine artifacts. Aztec legends include Huitzilopochtli, the god of the sun and war, whose journeys across the sky were seen as a daily cycle of life, death, and rebirth. This cyclical view of time was central to their cosmology. Japanese folklore tells of Urashima Taro, a fisherman who visits an undersea palace and returns to find centuries have passed. This tale emphasizes the relative nature of time experienced in different realms. The myths of the Sumerians, one of the earliest civilizations, include gods like Enki who could alter the course of events, effectively manipulating time. These stories reflect an early recognition of time's fluidity. In the Incan Empire, time was viewed as a sacred element, with gods like Inti, the sun god, controlling its passage. Their legends often involved divine beings traveling across time to shape human destiny. African tribal myths frequently feature trickster figures like Anansi, who could manipulate time to outwit others. These stories highlight the cunning use of temporal knowledge as a form of power. Across cultures, these ancient myths and legends reveal a profound human fascination with time travel, suggesting that the desire to move through time is a universal theme that has captivated minds throughout history. Philosophers have long pondered the nature of time and the possibility of moving through it. These early debates laid the groundwork for our modern understanding of temporal mechanics and the concept of time travel. Ancient Greek philosopher Heraclitus proposed that time is like a river, constantly flowing and never the same twice. This idea suggests that time is in a constant state of flux, an endless progression of moments. Parmenides, on the other hand, argued that time is an illusion and that reality is unchanging and eternal. His perspective challenges the very foundation of time travel, implying a static universe where movement through time is impossible. Plato introduced the concept of eternal forms, suggesting that true reality exists outside of time. For Plato, the temporal world we experience is just a shadow of this timeless realm, hinting at the possibility of transcending time. Aristotle, however, viewed time as a measure of change, intimately connected to the motion of objects. His practical approach to time laid the groundwork for future scientific inquiry into how time operates. St. Augustine of Hippo grappled with the nature of time in his writings, famously questioning whether the past and future truly exist. He concluded that time is a subjective experience, existing only in the mind. Medieval philosophers like Thomas Aquinas explored the idea of God's relationship with time, proposing that an omnipotent being exists outside of temporal constraints. This theological perspective implies a dimension beyond human time. In the Renaissance, thinkers like Giordano Bruno speculated about the infinite nature of the universe and the potential for multiple timelines. His ideas foreshadowed modern multiverse theories, suggesting a plurality of times. Sir Isaac Newton revolutionized the understanding of time by defining it as absolute and universal, flowing uniformly regardless of external factors. This Newtonian view dominated scientific thought for centuries. In contrast, Gottfried Wilhelm Leibniz argued that time is relational, dependent on the events that occur within it. This perspective paved the way for more dynamic and relative concepts of time. Immanuel Kant proposed that time is a fundamental framework of human perception, structuring our experiences, but not existing independently of them. This idea suggests that time travel would require altering our very perception of reality. Hegel's philosophy introduced the concept of historical progress, viewing time as a dialectical process of development. His ideas imply a forward-moving trajectory of time, integral to the evolution of human consciousness. The 19th century saw the emergence of phenomenology, with philosophers like Edmund Husserl examining the structures of temporal experience. This introspective approach to time influenced later existentialist and modernist thought. Henry Bergson emphasized the difference between measured time and lived time, or duration, arguing that true time is experienced subjectively. His work highlighted the qualitative aspects of time, beyond mere numerical measurement. Friedrich Nietzsche's concept of eternal recurrence proposed that time is cyclical, with events repeating infinitely. This radical idea challenges linear notions of time, opening up intriguing possibilities for time travel. As we continue our exploration, we see how these early philosophical debates have profoundly influenced contemporary discussions about the nature and possibility of time travel. The 19th century marked the birth of modern science fiction, with time travel emerging as a central theme. Writers began to explore the possibilities of moving through time, blending scientific curiosity with imaginative storytelling. H.G. Wells' The Time Machine, published in 1895, is perhaps the most iconic early work of time travel fiction. Wells introduced the concept of a machine that could travel through time, setting the stage for countless future stories. Jules Verne, known for his visionary tales, also dabbled in temporal themes. While not focused exclusively on time travel, his works often included elements of advanced technology and speculative science that hinted at temporal possibilities. Edward Page Mitchell's short story, The Clock That Went Backward, published in 1881, features a clock that allows its owners to travel back in time. This lesser-known work predates Wells and explores the implications of altering past events. Mark Twain's A Connecticut Yankee in King Arthur's Court, published in 1889, tells the story of a modern man transported to medieval times. Twain used time travel to satirize contemporary society and explore historical contrasts. In the late 19th century, the concept of time travel began to fascinate both writers and readers. The era's scientific advancements and changing worldviews provided fertile ground for these imaginative explorations. The notion of time as a dimension that could be traversed, much like space, started to gain traction. This idea was revolutionary, challenging traditional perceptions of time as a linear and unalterable sequence. These early science fiction stories often grappled with the paradoxes and consequences of time travel. Writers speculated about the potential dangers and ethical dilemmas of altering the past or knowing the future. The 19th century literary landscape was rich with experimentation and innovation. Authors used time travel as a narrative device to explore deeper philosophical questions about human existence and destiny. These pioneering works laid the foundation for the genre of time travel fiction. They sparked the imaginations of future generations of writers, inspiring them to further push the boundaries of what was scientifically and narratively possible. The fascination with time travel reflected broader societal changes of the 19th century. Rapid advancements in technology and industry made the concept of manipulating time seem increasingly plausible and intriguing. As new scientific theories emerged, they influenced the ways writers conceptualized time travel. The blending of scientific knowledge with literary creativity allowed for richer and more plausible depictions of temporal journeys. These stories also mirrored the anxieties and aspirations of their time. Through time travel, writers could address contemporary concerns, such as the impact of technological progress and the nature of human progress. The popularity of time travel tales in the 19th century set the stage for the genre's explosive growth in the 20th century. It became a staple of science fiction, continuously evolving with new scientific discoveries and cultural shifts. As we delve deeper into the science and theories behind time travel, we'll see how these early literary explorations have shaped our understanding and kept the dream of time travel alive through the ages. Albert Einstein's theory revolutionized our understanding of time and space. Introduced in the early 20th century, it challenged the conventional views of time as a constant and unchanging entity. Einstein's special theory of relativity, published in 1905, proposed that time is relative and can vary depending on the observer's speed. This concept, known as time dilation, suggests that time can slow down or speed up based on how fast one is moving. A key aspect of special relativity is that the speed of light is constant and the same for all observers, regardless of their motion. This constancy leads to the conclusion that time and space are intertwined in a four-dimensional continuum called space-time. Einstein further developed these ideas in his general theory of relativity, published in 1915. This theory describes gravity not as a force, but as a curvature of space-time caused by mass and energy. According to general relativity, massive objects like stars and planets warp the space-time around them. This warping affects the passage of time, making it run slower in stronger gravitational fields, a phenomenon known as gravitational time dilation. Einstein's theories have been confirmed by numerous experiments and observations. For instance, precise measurements of time using atomic clocks on airplanes and satellites have demonstrated the effects of both time dilation and gravitational time dilation. These discoveries have profound implications for the possibility of time travel. If time can be stretched and compressed, it might be possible to manipulate it to travel to the past or future. One of the most intriguing solutions to Einstein's equations of general relativity is the concept of a wormhole. Wormholes are hypothetical tunnels through space-time that could connect distant points, potentially allowing for instant travel across both space and time. Another theoretical possibility arising from relativity is the concept of closed, time-like curves. These curves are paths through space-time that loop back on themselves, theoretically allowing an object to return to its own past. However, the practical challenges of creating and maintaining a stable wormhole or closed time-like curve are immense. They would require exotic matter with negative energy density, something that has not yet been observed. Einstein himself was skeptical about the feasibility of time travel, particularly because of the paradoxes it could create. Nevertheless, his theories have opened the door to serious scientific inquiry into the nature of time and the potential for traveling through it. The concept of time dilation also plays a crucial role in modern technologies such as GPS. Satellites in orbit experience different gravitational forces and velocities compared to those on Earth, and their clocks must be adjusted for relativistic effects to provide accurate positioning data. The implications of Einstein's relativity extend far beyond time travel. They have reshaped our understanding of the universe, influencing everything from the behavior of black holes to the expansion of the cosmos. As we continue to explore the potential of time travel, Einstein's theories remain a cornerstone. They provide the scientific framework that guides current research and fuels the imagination of those dreaming of moving through time. The journey into the heart of relativity reveals a universe far stranger and more flexible than we ever imagined. It shows us that time is not an absolute, but a dynamic and integral part of the fabric of reality. Einstein's theory of relativity has had a profound impact on modern scientific thought, reshaping our understanding of the universe. It has influenced various fields, from cosmology to particle physics, providing a foundation for new discoveries. One of the most significant impacts is on our understanding of black holes. Relativity predicts the existence of these objects, where gravity is so strong that not even light can escape, warping space-time to an extreme degree. The theory has also changed how we view the expansion of the universe. General relativity describes how space-time itself can stretch, leading to the discovery that the universe is expanding, a finding supported by the observed redshift of distant galaxies. Relativity has influenced the development of technologies such as GPS. The precise timing required for GPS satellites to provide accurate positioning relies on adjustments for both special and general relativistic effects. In particle physics, relativity is essential for understanding the behavior of particles at high speeds. The Large Hadron Collider, the world's most powerful particle accelerator, operates under principles derived from relativistic physics. Quantum mechanics, another cornerstone of modern physics, has been examined in the context of relativity, leading to attempts to unify the two theories. This ongoing quest has given rise to concepts like quantum field theory and string theory. Einstein's work has also inspired theoretical physicists to explore the possibility of time travel. While practical time travel remains speculative, relativity provides the mathematical framework to consider such scenarios seriously. Relativity has reshaped our understanding of gravity, moving from Newton's idea of a force acting at a distance to a curvature of space-time. This new perspective has led to deeper insights into the nature of gravitational waves, recently detected by LIGO. The concept of space-time itself has become a fundamental aspect of how we understand the universe. This four-dimensional framework has replaced older, more limited views of space and time as separate entities. Relativity has influenced philosophical discussions about the nature of reality and the passage of time. Philosophers and scientists alike have grappled with the implications of a universe where time is relative and not absolute. In cosmology, general relativity has provided the tools to understand phenomena such as the Big Bang and cosmic inflation. These concepts explain the origins and early development of the universe in ways that were previously unimaginable. The theory has also led to the prediction and subsequent discovery of exotic astrophysical objects, such as neutron stars and quasars. These discoveries have expanded our knowledge of the universe's most extreme environments. Einstein's equations have been crucial in the development of modern astrophysics. They help scientists model the behavior of stars, galaxies, and the large-scale structure of the cosmos, revealing the dynamic and interconnected nature of the universe. The influence of relativity extends to everyday technologies, from medical imaging techniques like MRI to the synchronization of timekeeping systems across the globe. These practical applications highlight the theory's far-reaching impact. As we look to the future, the principles of relativity continue to guide scientific exploration. Whether probing the depths of black holes or seeking to understand the nature of dark matter and dark energy, relativity remains central to our quest to comprehend the cosmos. General relativity, proposed by Einstein in 1915, revolutionized our understanding of gravity. It replaced Newton's law of universal gravitation with a new theory that describes gravity as the curvature of space-time caused by mass and energy. In general relativity, massive objects like stars and planets warp the fabric of space-time around them. This curvature affects the motion of other objects, causing them to move along curved paths, which we perceive as gravitational attraction. Space-time itself is a four-dimensional continuum, integrating the three dimensions of space with the dimension of time. This concept fundamentally changes how we think about the structure of the universe and the nature of time. One of the key insights of general relativity is that time passes differently in regions of different gravitational strength. Near a massive object, time slows down compared to regions with weaker gravity, a phenomenon known as gravitational time dilation. Einstein's field equations describe how matter and energy determine the curvature of space-time. These complex equations have been used to predict a wide range of astrophysical phenomena, from the bending of light around stars to the expansion of the universe. The theory also predicts the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These mysterious objects are formed when massive stars collapse under their own gravity. Another prediction of general relativity is the existence of gravitational waves. These ripples in space-time travel at the speed of light, carrying information about catastrophic events such as collisions of black holes or neutron stars. The detection of gravitational waves by LIGO in 2015 confirmed a major prediction of general relativity. This discovery has opened a new way to observe the universe, allowing us to detect and study phenomena that were previously invisible. General relativity also describes the phenomenon of frame dragging, where rotating massive objects twist the space-time around them. This effect has been confirmed by observations of the Earth and other celestial bodies. One of the most fascinating aspects of general relativity is its implication for the nature of time travel. The theory allows for solutions like wormholes and closed time-like curves, which could, in principle, permit travel between different points in time. Space-time diagrams are a useful tool for visualizing the effects of general relativity. These diagrams depict how objects move through the four-dimensional fabric of space-time, illustrating concepts like geodesics and event horizons. The concept of space-time curvature has also led to the idea of a finite but unbounded universe. This means that while the universe might have a finite volume, you could travel indefinitely without ever encountering a boundary. General relativity has transformed our understanding of cosmology, providing a framework for the Big Bang theory and models of the universe's expansion. It explains how the universe has evolved over billions of years, from a hot, dense state to its current form. The influence of general relativity extends beyond astronomy and cosmology. It plays a crucial role in modern GPS technology, as the system must account for the relativistic effects of both special and general relativity to provide accurate positioning data. As we delve deeper into the mysteries of the cosmos, general relativity remains a vital tool. It continues to shape our understanding of the universe, offering insights into the fundamental nature of reality and the interconnected fabric of space and time. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts between distant points. They were first proposed by Albert Einstein and Nathan Rosen in 1935 as a solution to the equations of general relativity. A wormhole can be visualized as a tunnel, with two ends at separate points in space-time. If such a structure exists, it could potentially allow for faster-than-light travel between its two ends, bypassing the conventional limits of distance and time. The mouth of a wormhole is typically depicted as a sphere, while the tunnel itself might be thought of as a narrow tube connecting different regions of the universe. These structures, if stable, could revolutionize our understanding of travel and communication. One of the major challenges in realizing wormholes is their stability. Theoretical models suggest that maintaining an open wormhole would require exotic matter with negative energy density, something not yet observed in nature. The concept of exotic matter stems from quantum field theory, where certain conditions might allow for the creation of negative energy. However, the practical production and control of such matter remain purely speculative. Wormholes are also hypothesized to be extremely small, possibly on the order of subatomic particles. Enlarging a wormhole to a usable size would involve significant technological advancements far beyond our current capabilities. Despite these challenges, wormholes continue to capture the imagination of scientists and science fiction writers alike. They offer tantalizing possibilities for time travel, interstellar exploration, and instantaneous communication. If a wormhole could connect two distant points in space, it might also link different points in time. This raises intriguing possibilities for time travel, although it also introduces complex paradoxes and potential causal violations. The theoretical framework for wormholes comes from solutions to the Einstein field equations. These solutions, known as Schwarzschild wormholes or Einstein-Rosen bridges, describe a specific type of spacetime curvature. In a Schwarzschild wormhole, the tunnel-like structure is formed by a black hole and a white hole. A white hole is a theoretical counterpart to a black hole, expelling matter and energy rather than absorbing it. Another type of wormhole, known as a traversable wormhole, was proposed by physicist Kip Thorne and his colleagues. Unlike Schwarzschild wormholes, traversable wormholes would not collapse into a singularity, making them potentially usable for travel. The concept of traversable wormholes relies heavily on the existence of negative energy or exotic matter. Without this, the immense gravitational forces would cause the wormhole to collapse almost instantaneously. The study of wormholes intersects with various fields of theoretical physics, including quantum mechanics and string theory. These disciplines offer potential insights into the fundamental nature of spacetime and the conditions required for wormhole stability. While no experimental evidence for wormholes exists, their theoretical exploration provides valuable insights into the nature of gravity, spacetime, and the limits of our physical laws. They challenge our understanding and push the boundaries of what might be possible. As we continue to investigate the mysteries of the universe, wormholes remain a topic of intense interest and speculation. They represent one of the most fascinating and challenging frontiers in modern physics, holding the promise of unlocking new dimensions of reality. Cosmic strings are hypothetical one-dimensional defects in the fabric of spacetime. They are believed to have formed during the early universe, moments after the Big Bang, as the universe underwent phase transitions. These strings are incredibly thin, with widths much smaller than a proton, yet they possess immense mass and tension. A cosmic string stretching across the universe could have a mass equivalent to that of a large planet per unit length. Cosmic strings are predicted by various theories in particle physics, particularly those involving the early universe's symmetry-breaking processes. They are similar to cracks that form when water freezes into ice, representing imperfections in the structure of spacetime. One of the intriguing aspects of cosmic strings is their potential to warp spacetime around them. This warping could create gravitational fields strong enough to affect the movement of objects and the flow of time near the string. If two cosmic strings were to collide or form a loop, they could create powerful gravitational waves. These waves would ripple through spacetime, potentially detectable by instruments like LIGO and Virgo. Some theories suggest that cosmic strings could connect different regions of the universe, acting as cosmic highways. This could make them relevant to discussions of faster-than-light travel and even time travel. Theoretical models predict that cosmic strings would produce distinct gravitational lensing effects. Light passing near a cosmic string would be bent, creating double images of distant objects, a phenomenon that could help astronomers identify these elusive structures. In addition to gravitational lensing, cosmic strings might leave imprints on the cosmic microwave background. These imprints could provide clues about the conditions of the early universe and the presence of cosmic strings. Cosmic strings could also influence the formation of galaxies and other large-scale structures. Their immense gravitational pull might help seed the initial clumping of matter that eventually led to galaxy formation. Despite their theoretical significance, cosmic strings have not yet been observed. Detecting them would require highly sensitive instruments capable of measuring their subtle gravitational effects over vast distances. Research into cosmic strings continues to push the boundaries of our understanding of fundamental physics. They provide a unique window into the conditions of the early universe and the nature of space-time itself. The study of cosmic strings intersects with various fields including cosmology, particle physics, and general relativity. This interdisciplinary approach helps scientists develop more comprehensive models of the universe. Cosmic strings also appear in certain models of string theory. In these models, the fundamental building blocks of the universe are one-dimensional strings, and cosmic strings represent large-scale manifestations of these tiny entities. The search for cosmic strings involves both theoretical and observational efforts. Scientists use computer simulations to predict their properties and behavior, while astronomers analyze data from telescopes and gravitational wave detectors. As we continue to explore the universe, the discovery of cosmic strings would be a groundbreaking achievement. It would confirm key aspects of our theoretical models and provide new insights into the fundamental nature of reality. Quantum mechanics introduces a fundamentally different view of the universe, focusing on the behavior of particles at the smallest scales. This field of physics has opened new possibilities and challenges for the concept of time travel. One of the core principles of quantum mechanics is superposition, where particles can exist in multiple states simultaneously. This concept has led to speculation about multiple timelines or parallel universes. Quantum entanglement, another key phenomenon, describes how particles can become linked, instantly affecting each other regardless of distance. This spooky action at a distance, as Einstein called it, hints at deeper connections within the fabric of reality. Some theories propose that quantum entanglement could enable communication across time, not just space. If true, this might offer a mechanism for sending information to the past or future. The famous thought experiment known as Schrödinger's cat illustrates the strange nature of quantum mechanics. A cat in a box can be simultaneously alive and dead until observed, suggesting that outcomes in quantum systems can depend on observation. Quantum mechanics also introduces the concept of probability, where outcomes are not deterministic, but instead described by likelihoods. This probabilistic nature raises questions about predictability and causality in time travel scenarios. One intriguing idea is that quantum computers, which leverage superposition and entanglement, could simulate complex quantum systems, potentially including different timelines. These simulations might provide insights into the nature of time itself. Hugh Everett's many worlds interpretation suggests that every quantum event spawns a new branching universe. This interpretation implies an ever-growing multiverse, where each possible outcome of a quantum event is realized in a separate universe. The many worlds interpretation has profound implications for time travel. It suggests that traveling to the past might create a new branch of reality, avoiding paradoxes by diverging into a different timeline. Quantum field theory, which extends quantum mechanics to fields like electromagnetism, also plays a role in understanding time travel. It provides a framework for considering how particles and forces interact across space-time. Stephen Hawking proposed the chronology protection conjecture, arguing that the laws of physics prevent macroscopic time travel. However, the quantum realm might offer exceptions, where tiny particles could briefly travel through time. Research into quantum gravity seeks to unify general relativity and quantum mechanics, potentially revealing new aspects of space-time. This unified theory could offer insights into how time travel might be possible at quantum scales. Quantum tunneling, where particles pass through barriers they seemingly shouldn't, hints at shortcuts through space-time. Some scientists speculate that tunneling could be related to time travel at the quantum level. Decoherence, a process where quantum systems lose their quantum properties through interaction with their environment, challenges the practical realization of quantum time travel. It underscores the delicate nature of maintaining quantum states. As we continue to explore quantum mechanics, the potential for time travel remains one of its most fascinating and controversial aspects. The interplay between the quantum world and our understanding of time offers a rich field for future discoveries. Stephen Hawking proposed the chronology protection conjecture to address the potential paradoxes of time travel. This idea suggests that the laws of physics prevent the occurrence of closed time-like curves, which would allow time travel to the past. Hawking's conjecture argues that if closed time-like curves were possible, they could lead to inconsistencies and paradoxes. These include scenarios like the grandfather paradox, where a time traveler could potentially alter events in a self-contradictory way. According to the chronology protection conjecture, the universe has mechanisms to prevent such paradoxes. These mechanisms might include physical laws or constraints that make time travel to the past fundamentally impossible. Hawking suggested that the energy required to create closed time-like curves would be so immense that it would cause the region to collapse into a singularity. This collapse would effectively block any time travel attempts. Quantum effects also play a role in Hawking's conjecture. He proposed that quantum fluctuations would become so intense near a would-be time machine that they would disrupt the formation of closed time-like curves. The concept of chronology protection aligns with general relativity, which predicts the behavior of space-time under extreme conditions. It ensures that causality, the principle that cause precedes effect, is preserved throughout the universe. Hawking's conjecture does not rule out all forms of time travel, particularly those involving travel to the future. According to relativity, traveling at high speeds or near massive objects can slow down time, allowing a kind of forward time travel. While the chronology protection conjecture has gained support, it remains a topic of debate among physicists. Some researchers believe that loopholes or exceptions to the conjecture might exist, allowing for limited forms of time travel. Hawking's work on chronology protection has influenced how scientists approach the idea of time travel. It provides a framework for understanding the constraints imposed by the laws of physics and helps guide the search for viable time travel theories. The conjecture has implications for the study of black holes, where extreme gravitational effects could create conditions conducive to closed time-like curves. Hawking's ideas suggest that even in these extreme environments, time travel paradoxes would be avoided. In addition to black holes, the chronology protection conjecture applies to other exotic structures, like wormholes. It implies that any wormhole capable of time travel would encounter physical barriers, preventing paradoxical situations. Hawking's conjecture also touches on the nature of quantum mechanics and general relativity. The interplay between these two fundamental theories continues to challenge our understanding of spacetime and causality. The idea of chronology protection extends beyond theoretical physics into philosophical discussions about the nature of time and reality. It raises questions about the limits of human knowledge and the potential for technological advancements. Hawking's work has inspired further research into the nature of time, encouraging scientists to explore new models and theories. His conjecture remains a guiding principle in the quest to understand the fundamental structure of the universe. As we continue to investigate the possibilities of time travel, Hawking's chronology protection conjecture reminds us of the inherent complexities and paradoxes involved. It challenges us to think critically about the nature of time and our place within it. Forward time travel, unlike traveling to the past, aligns well with our current understanding of physics. It relies on principles such as time dilation, as predicted by Einstein's theory of relativity. Time dilation occurs when an object moves at a significant fraction of the speed of light. For an observer traveling at such high speeds, time would pass more slowly compared to someone at rest. Astronauts aboard the International Space Station experience a tiny amount of time dilation. Due to their high orbital speeds, they age slightly slower than people on Earth, showcasing forward time travel on a very small scale. In theory, if a spacecraft could travel near the speed of light, the time dilation effect would become much more pronounced. The crew could experience only a few years while decades pass on Earth. This concept is beautifully illustrated in the movie Interstellar, where astronauts traveling near a black hole experience time much slower than people on Earth. Such scenarios are based on solid scientific principles. Another way to achieve forward time travel involves intense gravitational fields. According to general relativity, time passes more slowly near massive objects, like black holes or neutron stars. If you were to orbit close to a black hole without falling in, you would experience significant time dilation. Time for you would slow down relative to people far away from the black hole's gravity. One of the most profound implications of forward time travel is the potential to see the future. By traveling at high speeds or near strong gravitational fields, a traveler could leap years, centuries, or even millennia ahead. Practical implementation of forward time travel requires overcoming immense technological challenges. Building spacecraft capable of near light-speed travel or surviving intense gravitational fields is far beyond our current capabilities. Forward time travel also presents fascinating possibilities for space exploration. A journey to distant stars might take a human lifetime from the perspective of the travelers, but much longer from the perspective of those on Earth. This type of time travel avoids the paradoxes associated with backward time travel. Since it doesn't involve altering past events, it aligns neatly with our understanding of causality. Despite the challenges, forward time travel has inspired numerous scientific studies and science fiction stories. It represents a realm where imagination meets the limits of physical law. The concept encourages us to think about the future and the nature of human existence. It raises questions about what it means to age, experience time, and perceive the passage of life. While forward time travel on a significant scale remains theoretical, the basic principles are supported by robust scientific evidence. It stands as a testament to the power of human curiosity and our quest to understand the universe. As technology advances, who knows what the future might hold for forward time travel? It's a field ripe with potential, awaiting the next breakthroughs that could turn science fiction into reality. Backward time travel, the idea of moving from the present to the past, poses more significant challenges and paradoxes. Unlike forward time travel, it involves potential alterations to events that have already occurred. One of the most famous paradoxes is the grandfather paradox. If someone travels back in time and prevents their grandparents from meeting, it raises the question of how the time traveler could exist in the first place. To address these paradoxes, some theories suggest the existence of parallel universes. According to this idea, traveling back in time might create a new, divergent timeline, leaving the original timeline unchanged. Another concept is the Novikov self-consistency principle. This principle proposes that any actions taken by a time traveler in the past were always part of history, ensuring that paradoxical situations cannot occur. The idea of closed time-like curves emerges from solutions to Einstein's equations in general relativity. These curves represent paths in space-time that loop back on themselves, theoretically allowing for backward time travel. Wormholes, if they exist and can be stabilized, offer another potential means for backward time travel. A wormhole could connect different points in time, but this would require exotic matter and immense energy. Quantum mechanics introduces further complexities with the notion of quantum superposition. Some theories suggest that backward time travel could involve quantum states that exist in multiple times simultaneously. The idea of backward time travel has been explored extensively in science fiction. Stories like H.G. Wells's The Time Machine and movies like Back to the Future highlight the dramatic and often humorous consequences of altering the past. Some physicists speculate that backward time travel might be possible at the quantum level. Quantum particles, unlike macroscopic objects, might exhibit behaviors that allow for limited backward temporal movement. Despite these fascinating theories, no experimental evidence supports the feasibility of backward time travel. It remains a speculative and highly theoretical area of study within physics. Research into backward time travel often intersects with studies of black holes and the nature of space-time. These extreme environments provide the conditions where the boundaries of known physics are pushed. The concept also raises profound philosophical questions about determinism and free will. If the past can be changed, it challenges our understanding of causality and the linear progression of time. Backward time travel, while theoretically intriguing, is fraught with technical and conceptual hurdles. Stabilizing a wormhole or creating closed time-like curves involves overcoming barriers that currently seem insurmountable. Even if backward time travel were possible, it might be limited by physical constraints that prevent significant alterations to history. This could mean that any changes made would be self-consistent with the timeline we observe. As we explore the potential of backward time travel, It serves as a reminder of the complex and often paradoxical nature of time itself. It challenges us to rethink our assumptions and consider the deeper implications of temporal movement. Closed time-like curves are a concept from general relativity that describe paths in space-time which loop back on themselves. These curves theoretically allow an object to return to its own past, creating a loop in time. The existence of closed time-like curves implies that time travel to the past might be possible without violating the laws of physics. This idea challenges our traditional understanding of time as a linear, unidirectional flow. One of the key solutions to Einstein's field equations that allow closed time-like curves is the Gödel metric. Proposed by Kurt Gödel in 1949, this solution describes a rotating universe where time travel along closed time-like curves is possible. Another theoretical model involves rotating black holes, also known as Kerr black holes. The rotation of these black holes could create regions where closed time-like curves exist, potentially allowing time travel to the past. The concept of closed time-like curves raises significant paradoxes such as the grandfather paradox. These paradoxes question how events can unfold consistently if a time traveler can alter the past. To address these paradoxes, some physicists propose the Novikov self-consistency principle. This principle suggests that any actions taken by a time traveler were always part of history, thus avoiding contradictions. Theoretical models also consider the impact of quantum mechanics on closed time-like curves. Quantum effects could play a role in resolving paradoxes, but the interplay between quantum mechanics and general relativity remains a major challenge. Closed time-like curves are not just theoretical curiosities. They have practical implications for our understanding of the universe. They prompt us to explore the fundamental nature of time, causality, and the structure of space-time. One intriguing possibility is that closed time-like curves could be used to send information to the past. This would have profound implications for communication and our ability to influence historical events. Experimental evidence for closed time-like curves is currently lacking, and creating the conditions necessary for their existence is beyond our current technological capabilities. However, they remain a rich area of theoretical research. The study of closed time-like curves intersects with other areas of physics, such as the search for a unified theory of quantum gravity. Understanding how these curves might exist could provide insights into the nature of space-time and the limits of our physical theories. Philosophically, closed time-like curves challenge our notions of free will and determinism. If the future and past are interconnected through these curves, it raises questions about our ability to influence events and the nature of fate. Science fiction often explores the concept of closed time-like curves, using them as a narrative device to create complex and intriguing stories about time travel. These stories reflect our fascination with the possibility of bending the rules of time. As researchers continue to investigate closed time-like curves, they push the boundaries of our understanding of the universe. Each new theoretical development brings us closer to answering some of the most profound questions about time and reality. While the practical realization of closed time-like curves remains speculative, their study provides valuable insights into the fundamental principles of physics. They remind us of the complex and often mysterious nature of the cosmos. The multiverse theory suggests that our universe is just one of many universes that exist simultaneously. Each universe within the multiverse may have its own distinct laws of physics and constants. This concept arose from several branches of theoretical physics, including quantum mechanics and string theory. The idea is that multiple universes could explain various phenomena that seem inexplicable within the context of a single universe. One interpretation of quantum mechanics that supports the multiverse theory is the many worlds interpretation. Proposed by Hugh Everett, this interpretation suggests that every quantum event spawns a new, branching universe. In the context of time travel, the multiverse theory offers a way to resolve paradoxes. If traveling back in time creates a new universe, actions taken by the time traveler would not affect the original timeline. The inflationary model of the universe also supports the multiverse theory. According to this model, different regions of space stopped inflating at different times, potentially creating isolated bubble universes. These bubble universes could have different physical properties, leading to a vast and diverse multiverse. Our universe might just be one bubble among countless others. String theory, which attempts to unify all fundamental forces, also predicts the existence of a multiverse. Different solutions to the equations of string theory could describe different universes with varying dimensions and physical laws. The concept of a multiverse challenges our understanding of reality. It suggests that the universe we observe is just a small part of a much larger and more complex structure. Evidence for the multiverse is currently indirect and speculative. However, certain observations, such as the cosmic microwave background radiation, have led some scientists to consider the multiverse as a plausible theory. If the multiverse exists, it could have profound implications for our understanding of existence. It raises questions about the nature of reality, the limits of human knowledge, and the potential for other forms of life. The multiverse theory also intersects with philosophical questions about the nature of existence. It suggests that there could be other versions of ourselves living different lives in parallel universes. Some scientists are exploring ways to test the multiverse theory. These efforts include looking for signatures of other universes in the cosmic microwave background or finding evidence of collisions between bubble universes. The multiverse theory offers an explanation for the fine-tuning of the constants of nature. If there are countless universes, it's not surprising that at least one, like ours, has the right conditions for life. Despite its speculative nature, the multiverse theory continues to inspire both scientific and philosophical inquiry. It encourages us to think beyond the confines of our observable universe. As we delve deeper into the mysteries of the cosmos, the multiverse theory remains a tantalizing possibility. It challenges us to expand our horizons and consider the vast and varied possibilities of existence. Parallel universes are a specific type of multiverse concept where every possible outcome of a decision or event creates a new, separate universe. These universes run parallel to each other, each representing different possibilities. The idea of parallel universes is closely related to the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event results in a branching of the universe into multiple, distinct paths. Each parallel universe would follow its own timeline, completely independent of the others. This means that different versions of events and different versions of people could exist simultaneously in these alternate realities. Parallel universes provide a way to address the paradoxes associated with time travel. If traveling back in time creates a new parallel universe, changes made by the traveler would not affect the original timeline they came from. This concept has been a popular subject in science fiction, inspiring countless stories and movies. These narratives explore the fascinating possibilities and ethical dilemmas of interacting with parallel realities. In theoretical physics, parallel universes are often considered within the framework of string theory and quantum mechanics. These fields suggest that multiple universes could exist as part of a larger multiverse structure. Evidence for parallel universes remains elusive, but some physicists propose that certain anomalies in cosmological data could hint at their existence. These include unexpected patterns in the cosmic microwave background radiation. The concept of parallel universes challenges our perception of reality and raises questions about the nature of existence. If parallel universes exist, it suggests that our reality is just one of many possible versions. Philosophically, parallel universes prompt us to think about the nature of choice and destiny. Each decision we make could potentially create a new universe, leading to a multitude of different life paths. The idea of parallel universes also intersects with the concept of alternate histories. These are speculative scenarios where historical events have different outcomes, leading to entirely different worlds. In the context of time travel, parallel universes offer a solution to the grandfather paradox. By creating a new universe, the time traveler avoids the paradoxical consequences of altering their own past. Research into parallel universes is ongoing, with scientists exploring various theoretical models and potential observational evidence. The development of new technologies and methods could eventually provide more insights. While parallel universes remain a speculative idea, they offer a rich field for scientific and philosophical exploration. They challenge us to rethink our understanding of reality and the limits of our knowledge. The concept of parallel universes also inspires discussions about the nature of consciousness and identity. If multiple versions of ourselves exist, It raises questions about what it means to be uniquely individual. As we continue to explore the possibilities of parallel universes, we push the boundaries of our imagination and scientific inquiry. The pursuit of understanding these alternate realities brings us closer to unraveling the mysteries of the cosmos. Experimental physics has provided concrete evidence for time dilation, a key concept in understanding the possibilities of time travel. Time dilation occurs when time moves slower for an object in motion compared to one at rest, as predicted by Einstein's theory of relativity. One of the most famous experiments demonstrating time dilation involved highly accurate atomic clocks. Clocks flown around the world on airplanes showed a measurable difference in time compared to those that remained on the ground. This effect is even more pronounced in particles moving at high speeds. Particles called muons, created by cosmic rays hitting the Earth's atmosphere, live longer when moving close to the speed of light compared to when they are at rest. Particle accelerators, such as the Large Hadron Collider, have also confirmed time dilation. Particles accelerated to near light speeds exhibit longer lifespans, validating the predictions of special relativity. The Global Positioning System, or GPS, relies on time dilation corrections to function accurately. Satellites in orbit experience less gravity and move faster than receivers on Earth, requiring adjustments for both gravitational and velocity-based time dilation. Astronauts aboard the International Space Station experience time slightly slower than people on Earth due to their high orbital speeds. This real-world example highlights the practical implications of time dilation in human spaceflight. Experiments involving high-velocity particles have shown that time dilation increases with speed. As particles approach the speed of light, the effect becomes more significant, supporting the theoretical framework of relativity. Gravitational time dilation, another aspect of relativity, occurs near massive objects. Experiments with precise clocks placed at different altitudes confirm that clocks closer to Earth's surface run slower than those at higher elevations. Tests of general relativity using atomic clocks on mountaintops and in deep mines have provided further confirmation. These experiments show that time dilation due to gravity is a real and measurable phenomenon. High-precision measurements, such as those using optical lattice clocks, continue to refine our understanding of time dilation. These advanced clocks can detect minute differences in time flow, enhancing our ability to study relativistic effects. The Haffel-Keating experiment, conducted in the 1970s, provided early empirical evidence for time dilation. Atomic clocks flown eastward and westward around the Earth showed discrepancies consistent with relativistic predictions. Time dilation has also been observed in the decay rates of unstable particles. Particles moving at high velocities decay more slowly, a direct consequence of time dilation, and a confirmation of special relativity. Research into time dilation continues to push the boundaries of precision measurement. Advances in technology enable scientists to test the limits of relativity with increasing accuracy, providing deeper insights into the nature of time. Understanding time dilation is crucial for developing potential time travel technologies. While practical time travel remains a distant prospect, the principles of relativity guide our theoretical and experimental efforts in this field. As we explore the effects of time dilation, we gain a better grasp of how time operates under different conditions. These insights bring us closer to unraveling the complexities of time travel and the fundamental nature of the universe. GPS systems rely heavily on the principles of relativity to provide accurate positioning data. The satellites in orbit experience both special and general relativistic effects, which must be accounted for to maintain precision. Special relativity predicts that clocks on the satellites, moving at high speeds relative to the Earth, will run slower than clocks on the ground. This time dilation effect is crucial for synchronizing the satellite clocks with those on Earth. General relativity adds another layer of complexity. Satellites are farther from the Earth's gravitational field, so they experience less gravitational time dilation. This means that, according to general relativity, their clocks run faster compared to those on the Earth's surface. To ensure GPS accuracy, the system must correct for both special and general relativistic effects. Without these adjustments, the positioning errors would accumulate rapidly, rendering the system unreliable. The satellite's clocks are continually adjusted to account for the time dilation effects. These corrections ensure that the signals sent from the satellites are synchronized with the receivers on the ground. Each GPS satellite contains atomic clocks that provide the precise timing necessary for the system to function. These clocks are incredibly accurate but still require relativistic corrections to maintain synchronization. When a GPS receiver calculates its position, it measures the time delay from signals sent by multiple satellites. The accuracy of this timing is essential for determining the receiver's exact location on Earth. Relativity ensures that the timing from the satellites remains consistent with the receiver's clocks. By accounting for both the velocity of the satellites and their altitude, the system maintains the precision required for accurate positioning. The integration of relativity into GPS technology is a remarkable example of theoretical physics applied to practical use. It demonstrates how our understanding of time and space can directly impact everyday technologies. The success of GPS systems in incorporating relativistic effects underscores the importance of fundamental physics in engineering. This real-world application validates Einstein's theories and their relevance to modern technology. GPS technology continues to evolve, with newer satellites and improved algorithms enhancing accuracy. These advancements rely on our deepening understanding of relativistic effects and their impact on timekeeping. The principles of relativity are not just theoretical concepts, but are essential to the functionality of technologies we use daily. GPS is a prime example of how scientific theories translate into practical solutions. As we develop new technologies that rely on precise timing and positioning, the role of relativity will likely expand. Future systems may incorporate even more sophisticated corrections to account for relativistic effects. Understanding how GPS systems use relativity helps us appreciate the complexities involved in satellite navigation. It highlights the intricate balance between theory and application, ensuring that our positioning systems remain accurate and reliable. The integration of relativity into GPS technology showcases the enduring impact of Einstein's work. It illustrates the profound ways in which our understanding of the universe shapes and enhances the tools we depend on. High-energy particle accelerators are powerful tools that allow scientists to explore the fundamental particles and forces of the universe. These machines accelerate particles to near light speeds and then collide them, revealing the components and interactions of matter. One of the most famous particle accelerators is the Large Hadron Collider, or LHC, located at CERN in Switzerland. The LHC has been instrumental in discovering new particles, such as the Higgs boson, which helps explain why particles have mass. The extreme conditions within particle accelerators simulate environments that haven't existed since the early moments of the universe. By recreating these conditions, scientists can study how the universe evolved and understand the fundamental laws governing it. Particle collisions within accelerators produce vast amounts of data, revealing new insights about the nature of matter and energy. These high-energy impacts can generate exotic particles that are not typically found in nature. The discoveries made in particle accelerators often confirm or challenge existing theories in physics. For example, the confirmation of the Higgs boson provided critical evidence for the standard model of particle physics. Relativity plays a significant role in the operation of particle accelerators. As particles are accelerated to high speeds, they experience time dilation, making their internal processes appear to slow down from the perspective of an outside observer. The energies involved in particle collisions are immense, sometimes reaching levels that can create conditions similar to those just after the Big Bang. These high-energy environments are crucial for testing theoretical predictions in particle physics. Advancements in accelerator technology continue to push the boundaries of what can be observed and measured. Each new generation of accelerators provides deeper insights into the subatomic world and the fundamental forces of nature. High-energy particle accelerators also contribute to practical applications, such as in medical imaging and cancer treatment. The technology developed for particle physics research often leads to innovations in other fields. The data collected from particle accelerators help scientists refine existing models and develop new theories. This iterative process of experimentation and theory building is essential for advancing our understanding of the universe. One of the challenges in operating particle accelerators is managing the intense energy and radiation produced during collisions. Advanced shielding and safety measures are essential to protect both the equipment and the researchers. International collaboration is a hallmark of particle accelerator projects. Scientists from around the world work together to design, build, and operate these complex machines, pooling resources and expertise to achieve common goals. The experiments conducted in high-energy particle accelerators often have long-term implications for our understanding of physics. Each discovery can open new avenues of research and lead to unforeseen technological advancements. Particle accelerators help address some of the most fundamental questions in physics, such as the nature of dark matter and the unification of forces. These questions drive the ongoing search for a deeper understanding of the universe. The role of particle accelerators in exploring the fundamental aspects of reality underscores their importance in scientific research. They represent the cutting edge of our quest to understand the building blocks of the cosmos and the forces that shape it. Observations of cosmic phenomena provide valuable insights into the nature of the universe and the laws that govern it. These observations often involve studying distant astronomical objects and events, offering a glimpse into the past. Telescopes, both ground-based and space-based, are essential tools for observing cosmic phenomena. Instruments like the Hubble Space Telescope have revolutionized our understanding of the universe by capturing detailed images of galaxies, nebulae, and other celestial objects. One of the most significant observations in cosmology is the cosmic microwave background radiation. This faint glow, left over from the Big Bang, provides a snapshot of the early universe and supports the Big Bang theory. Gravitational lensing, where massive objects like galaxies bend light from objects behind them, offers a unique way to study dark matter. This phenomenon helps map the distribution of dark matter, which cannot be observed directly. Observing supernovae, the explosive deaths of stars, gives insight into the life cycles of stars and the expansion of the universe. Type Ia supernovae in particular have been crucial for measuring cosmic distances and understanding dark energy. Black holes, especially those merging and producing gravitational waves, are another focus of cosmic observations. The detection of gravitational waves by LIGO and Virgo has opened a new way to study these enigmatic objects. Quasars, extremely luminous and active galactic nuclei, provide information about the early universe and the growth of supermassive black holes. Observations of quasars help scientists understand the evolution of galaxies. Gamma-ray bursts, among the most energetic events in the universe, are thought to result from massive star collapses or neutron-star mergers. These bursts provide clues about the most extreme physical conditions in the cosmos. Pulsars, rotating neutron stars emitting beams of radiation, serve as cosmic clocks. Their precise timing can test the limits of general relativity and detect gravitational waves from other sources. Cosmic rays, high-energy particles from space, offer insights into the processes occurring in supernovae and other energetic events. Studying these particles helps understand the high-energy universe. The observation of exoplanets, planets orbiting other stars, has expanded our understanding of planetary systems. Discovering exoplanets in habitable zones raises the possibility of finding life beyond Earth. Galactic surveys, mapping large portions of the sky, help understand the structure and distribution of galaxies. These surveys provide data on galaxy formation and the large-scale structure of the universe. Fast radio bursts, mysterious and brief bursts of radio waves, have puzzled astronomers since their discovery. Studying these bursts could reveal new information about the intergalactic medium and exotic astrophysical processes. Observations of cosmic phenomena continually challenge and refine our theories of the universe. Each new discovery adds to our understanding and often leads to more questions, driving further exploration and study. As technology advances, our ability to observe the cosmos in greater detail improves, promising even more profound discoveries. These observations are crucial for unlocking the secrets of the universe and understanding our place within it. The current scientific consensus on time travel is that traveling to the future is theoretically possible according to the principles of special and general relativity. Time dilation, as observed in high-speed travel and strong gravitational fields, supports this possibility. However, traveling to the past presents significant challenges and paradoxes that have yet to be resolved. Most physicists agree that backward time travel is far more speculative and may be impossible due to these unresolved issues. Many researchers are skeptical about the feasibility of backward time travel, Because it could violate causality. Causality is a fundamental principle where cause precedes effect, and violating this principle could lead to logical inconsistencies. The concept of closed time-like curves suggests a possible way to achieve backward time travel within general relativity. However, the physical realization of these curves is highly uncertain and may require conditions that are not practically achievable. Hawking's chronology protection conjecture argues that the laws of physics may inherently prevent the formation of closed time-like curves, thus protecting the universe from paradoxical situations. This conjecture is widely discussed but not yet proven. Wormholes are another theoretical method for time travel, potentially allowing travel between different points in time. These hypothetical structures would require exotic matter to remain stable, something that has not been observed. Quantum mechanics introduces additional complexities with concepts like superposition and entanglement. Some theories suggest that these quantum effects could play a role in time travel, but this remains highly speculative. The integration of quantum mechanics and general relativity, often referred to as quantum gravity, is a major area of research. A successful theory of quantum gravity could provide new insights into the nature of time and the possibilities of time travel. Experimental evidence for any form of time travel is currently lacking. While time dilation effects are well documented, no experiments have demonstrated the feasibility of moving backward in time or creating stable wormholes. Most physicists agree that while time travel is a fascinating concept, it remains largely within the realm of theoretical exploration. The practical and technological challenges are immense and currently beyond our capabilities. Theoretical models continue to evolve, and new discoveries in physics could change our understanding of time travel. Advances in particle physics, cosmology, and quantum mechanics may provide new avenues for exploration. Interdisciplinary research combining insights from different fields of physics, philosophy, and computer science could also contribute to our understanding. This collaborative approach may help address some of the fundamental questions surrounding time travel. Public interest in time travel continues to drive both scientific inquiry and popular culture. While scientific consensus remains cautious, the ongoing fascination with time travel inspires new generations of researchers and thinkers. Current scientific consensus acknowledges the theoretical foundations and speculative nature of time travel. Researchers continue to explore the boundaries of physics, pushing the limits of what we know and can imagine. As we advance in our understanding of the universe, the dream of time travel remains a powerful motivator. It challenges us to think beyond the present and explore the profound mysteries of time and space. The grandfather paradox is one of the most well-known paradoxes associated with time travel. It describes a situation where a time traveler goes back in time and prevents their grandfather from meeting their grandmother. If the grandfather never meets the grandmother, the time traveler's parent would never be born. This means the time traveler themselves would never be born, creating a logical contradiction. This paradox illustrates the potential problems with altering past events. It raises fundamental questions about causality and the consistency of the timeline. One way to address the grandfather paradox is through the concept of parallel universes. If time travel creates a new parallel timeline, changes made in the past would not affect the original timeline. In this scenario, the time traveler could prevent their grandfather's marriage in the new timeline without causing a paradox. The original timeline would remain unchanged, allowing the traveler to exist in their original reality. Another proposed solution is the Novikov self-consistency principle. This principle suggests that any actions taken by a time traveler were always part of history and cannot create contradictions. According to the Novikov principle, the time traveler's actions in the past are constrained to be self-consistent. They cannot change events in a way that would prevent their own existence. This means that even if the time traveler tries to prevent their grandparents from meeting, some other event would ensure that their parents are still born. The timeline would adjust to remain consistent. Quantum mechanics offers another perspective on the grandfather paradox. The many worlds interpretation suggests that each possible outcome of a quantum event creates a new universe. If time travel to the past is possible, it could result in the creation of a new universe, where the time traveler's actions lead to different outcomes. The original universe would not be affected. Despite these theoretical solutions, the grandfather paradox remains a challenging and thought-provoking problem. It highlights the complexities and potential contradictions inherent in the concept of backward time travel. The paradox also raises philosophical questions about free will and determinism. If the timeline is self-consistent, it suggests a deterministic universe where events are fixed and unchangeable. On the other hand, the idea of parallel universes supports the notion of free will, with each decision creating a new branch of reality. This perspective allows for multiple coexisting outcomes. The grandfather paradox continues to inspire both scientific and philosophical debates. It serves as a powerful reminder of the complexities involved in understanding time and causality. As we explore the possibilities of time travel, the grandfather paradox challenges us to think critically about the nature of reality. It encourages us to consider the profound implications of manipulating time and altering history. The bootstrap paradox is another intriguing time travel paradox. It occurs when an object or piece of information sent back in time becomes the cause of itself in the future. This paradox creates a circular cause and effect loop with no clear origin. It raises questions about the nature of causality and the flow of time. An example of the bootstrap paradox involves a time traveler who takes a book on quantum physics back to the past. In the past, the traveler gives the book to a young physicist, who then publishes it as their own work. The book exists in both the future and the past, but its origin is unclear. It was never actually created or written in the traditional sense. This paradox challenges our understanding of creation and existence. It suggests that information or objects can exist without a clear point of origin. The bootstrap paradox is sometimes referred to as a causal loop. These loops create situations where events are both the cause and effect of themselves. Science fiction often explores the bootstrap paradox to highlight the complexities of time travel. Stories involving predestination or self-fulfilling prophecies frequently rely on this concept. One theoretical way to resolve the bootstrap paradox is through the many worlds interpretation of quantum mechanics. Each action taken by a time traveler could create a new branch of reality. In this interpretation, the object or information may originate from a different timeline, avoiding the paradox. However, this raises questions about the interaction between different universes. The paradox also raises philosophical questions about the nature of knowledge and discovery. If information can be transferred through time without a clear origin, it challenges our understanding of intellectual creation. Some physicists propose that the bootstrap paradox might be resolved by the constraints of physical laws. These constraints could prevent the formation of causal loops in the first place. Others suggest that the universe may self-consistently adjust to avoid paradoxes. This idea aligns with the Novikov self-consistency principle, which posits that any actions taken by a time traveler are already part of history. Despite these theoretical solutions, the bootstrap paradox remains a compelling problem. It underscores the potential difficulties in reconciling time travel with our understanding of causality. The paradox also serves as a thought experiment, prompting deeper consideration of the implications of time travel. It challenges us to think about the boundaries of what is possible within the laws of physics. As with other time travel paradoxes, the bootstrap paradox highlights the intricate relationship between time, causality, and existence. It invites ongoing exploration and debate among scientists and philosophers. Studying the bootstrap paradox helps us appreciate the complexities of time travel and the fundamental nature of reality. It encourages us to continue questioning and probing the limits of our understanding. The Novikov self-consistency principle was proposed to address the paradoxes associated with time travel. It asserts that any actions taken by a time traveler were always part of history, and therefore cannot create contradictions. According to this principle, the timeline is consistent and self-correcting. Events unfold in such a way that paradoxes, like the grandfather paradox, cannot occur. If a time traveler attempts to change the past, the Novikov principle suggests that events will conspire to prevent any inconsistencies. This ensures that history remains unchanged in a self-consistent manner. This principle provides a framework for understanding time travel without violating causality. It implies that while time travel might be possible, the outcomes are predetermined and consistent with the timeline. An example of the Novikov principle in action could involve a time traveler trying to prevent a historical event. According to the principle, their actions would inadvertently ensure that the event still occurs. The principle aligns with deterministic views of the universe, where all events are fixed and unchangeable. It suggests that free will may be limited when it comes to altering the past. The Novikov self-consistency principle has been explored in various science fiction stories. These narratives often depict time travel scenarios where attempts to change the past result in fulfilling historical events rather than altering them. Critics of the principle argue that it imposes a deterministic view on time travel, limiting the potential for free will and alternate outcomes. They question whether the universe truly operates in such a self-correcting manner. Despite these criticisms, the principle offers a coherent way to think about time travel without encountering logical contradictions. It provides a solution to many of the paradoxes that arise from backward time travel. The principle also raises interesting questions about the nature of destiny and fate. If events are self-consistent and unchangeable, it suggests a universe governed by predetermined outcomes. In physics, the principle is used to explore theoretical models of time travel. Researchers examine whether the laws of physics allow for self-consistent solutions that prevent paradoxes. The Novikov principle intersects with quantum mechanics, where the many worlds interpretation offers an alternative view. While the Novikov principle supports a single, consistent timeline, the many worlds interpretation suggests multiple, branching realities. The principle can also be applied to thought experiments involving information and objects sent back in time. It implies that any such actions would need to be consistent with historical records and events. Understanding the Novikov self-consistency principle helps clarify the constraints and possibilities of time travel. It encourages use to think about how the universe might handle changes to the timeline. The principle remains a topic of debate and exploration in both theoretical physics and philosophy. It provides a fascinating lens through which to consider the nature of time, causality, and the potential for time travel. Temporal causality refers to the relationship between causes and effects within the context of time. It underpins our understanding of how events are ordered and how one event leads to another. In everyday experience, causality is straightforward. A cause precedes its effect. This linear sequence is fundamental to our perception of time and the unfolding of events. Time travel complicates this simple picture. If an effect can precede its cause, as suggested in some time travel scenarios, it challenges the very foundation of temporal causality. Paradoxes like the grandfather paradox and the bootstrap paradox directly confront these issues. They illustrate how traditional notions of cause and effect break down when considering backward time travel. The Novikov self-consistency principle aims to preserve temporal causality by ensuring that any actions taken by a time traveler are already part of history. This principle avoids paradoxes by maintaining a consistent timeline. In physics, maintaining temporal causality is crucial for the consistency of theories. Violations of causality could lead to logical contradictions and unpredictable consequences in physical models. Quantum mechanics introduces additional complexity with phenomena like entanglement and superposition. These effects suggest that particles can influence each other instantaneously, raising questions about the limits of causality. Relativity also plays a role in our understanding of temporal causality. The theory of relativity demonstrates that time is not absolute but relative, depending on the observer's frame of reference. In general relativity, the warping of space-time by massive objects can affect the flow of time. This warping introduces the possibility of closed time-like curves, where temporal causality could loop back on itself. The idea of closed time-like curves suggests that causality might not always be linear. Events could potentially influence each other in a cyclical manner, complicating our understanding of temporal order. Philosophically, temporal causality raises questions about free will and determinism. If events are predetermined and self-consistent, it suggests a universe where the future is fixed and unchangeable. Experiments in high-energy physics and cosmology continue to test the boundaries of causality. Researchers explore how particles behave under extreme conditions and whether violations of causality might be possible. The study of temporal causality is not only theoretical but has practical implications. Understanding causality is crucial for developing technologies like quantum computers and for interpreting data from experiments. As we delve deeper into the nature of time and causality, we uncover new layers of complexity. Each discovery prompts us to rethink our assumptions and explore the boundaries of what is possible. The exploration of temporal causality helps us grasp the fundamental structure of the universe. It challenges us to reconcile our intuitive understanding of time with the strange and often counterintuitive findings of modern physics. The ethical implications of time travel are profound and complex. If time travel were possible, it could lead to significant moral dilemmas and societal impacts. One major ethical concern is the potential to alter historical events. Changing the past could have unintended consequences, affecting countless lives and altering the course of history in unpredictable ways. The power to change past events raises questions about responsibility and accountability. Who should have the authority to decide which events to alter, and what criteria should guide these decisions? Time travel could also be used for personal gain, such as acquiring wealth or power by exploiting knowledge of future events. This potential for abuse poses significant ethical challenges. The possibility of creating alternate timelines introduces further ethical issues. Each new timeline could represent a different set of outcomes, raising questions about the moral status of these parallel worlds. Interfering with past events could erase entire branches of history, effectively nullifying the existence of individuals and cultures. This raises profound ethical questions about the right to exist. Time travel could also impact our understanding of justice and retribution. If crimes could be prevented before they occur, how should society address issues of guilt and punishment? The ethical implications extend to scientific research as well. Developing time travel technology could divert resources from other important areas, raising questions about the best use of scientific funding and expertise. Moreover, the potential risks associated with time travel experiments could be significant. Unintended consequences might arise, potentially causing harm to individuals or the fabric of space-time itself. The possibility of encountering future or past versions of oneself also poses ethical dilemmas. Interactions with other versions of oneself could lead to identity and existential crises. There are also concerns about the ethical treatment of beings from different timelines. Should they be considered as fully autonomous individuals with their own rights and responsibilities? Time travel might also affect our perception of free will and determinism. If future events can be known or altered, it challenges the notion that individuals are free to make their own choices. Ethical considerations also extend to privacy. The ability to observe or interact with people in different times could violate their privacy and autonomy, raising significant moral concerns. Addressing these ethical implications requires careful consideration and debate. It involves balancing the potential benefits of time travel against the risks and moral dilemmas it presents. As we continue to explore the theoretical possibilities of time travel, these ethical questions remain crucial. They remind us that scientific advancements must be guided by a strong ethical framework to ensure responsible and beneficial use. Spacecraft traveling near light speed represent a significant scientific and engineering challenge. Achieving such velocities would require immense energy and advanced propulsion systems beyond our current technology. One of the most promising concepts for near light speed travel is the use of antimatter as a fuel. Antimatter reactions produce vast amounts of energy, potentially enabling spacecraft to reach a significant fraction of light speed. Another potential method is the development of light sails, propelled by powerful lasers or solar radiation. These sails could gradually accelerate a spacecraft to incredible speeds over long distances. Relativity predicts that as a spacecraft approaches light speed, time dilation becomes significant. Time for the travelers would slow down relative to observers on Earth, effectively allowing forward time travel. This time dilation could make interstellar travel feasible within a human lifetime. Astronauts on a near light speed journey might experience only a few years of travel, while decades or centuries pass on Earth. However, traveling at such high speeds presents numerous technical challenges. One major issue is the impact of interstellar particles, which could damage or destroy a spacecraft moving at near-light speeds. Shielding a spacecraft from these high-energy collisions would require advanced materials and innovative design solutions. Researchers are exploring various methods to mitigate these risks. Another challenge is the immense energy required to reach and maintain near-light speeds. Current propulsion technologies are insufficient, necessitating breakthroughs in energy generation and propulsion. As a spacecraft approaches light speed, its mass effectively increases, requiring even more energy to continue accelerating. This relativistic mass increase is a fundamental obstacle to achieving light-speed travel. Communication with a near-light-speed spacecraft would also be complex. The time dilation effects would make real-time communication with Earth difficult, requiring new protocols and technologies for managing delayed responses. Navigating at such high speeds would demand precise instrumentation and control systems. Small errors in trajectory could result in catastrophic outcomes, highlighting the need for highly accurate navigation technology. Despite these challenges, the concept of near-light-speed travel inspires ongoing research and innovation. Advances in fields such as fusion energy, advanced materials, and quantum computing could eventually make such travel possible. Near-light-speed travel also has profound implications for our understanding of the universe. It could enable exploration of distant star systems and potentially reveal new insights about the nature of space and time. As scientists and engineers work toward this ambitious goal, international collaboration will be essential. The development of near-light-speed spacecraft will likely require the combined efforts of the global scientific community. Achieving near-light-speed travel represents one of humanity's greatest technological aspirations. It promises to expand our horizons, enabling us to explore the cosmos in ways previously confined to the realm of science fiction. Wormhole engineering is a theoretical field focused on creating and stabilizing wormholes for practical use. These hypothetical passages through space-time could provide shortcuts between distant points in the universe. A key challenge in wormhole engineering is maintaining the stability of a wormhole. Theoretical models suggest that exotic matter with negative energy density is needed to keep a wormhole open. Exotic matter has properties that defy conventional physics, such as negative mass. While it has not been observed in nature, its existence is a critical component for wormhole stability. Generating and sustaining exotic matter would require technology far beyond our current capabilities. Researchers are exploring the theoretical foundations and potential methods for creating this exotic matter. Another challenge is the immense gravitational forces near the mouth of a wormhole. These forces could potentially destroy anything trying to pass through, requiring advanced shielding and structural integrity solutions. Wormhole mouths would need to be precisely positioned and aligned. Misalignment could result in catastrophic failures, making precise control mechanisms essential for wormhole navigation. Theoretical physicist Kip Thorne has suggested that traversable wormholes could exist without violating the known laws of physics. His work has inspired both scientific research and science fiction narratives. Energy requirements for creating a wormhole are immense. Some estimates suggest it would take the energy equivalent of several stars to create a stable, human-sized wormhole. Quantum effects add another layer of complexity to wormhole engineering. Quantum fluctuations could destabilize a wormhole, requiring mechanisms to counteract these effects. Even if a stable wormhole could be created, entering and exiting it safely poses significant challenges. The intense gravitational gradients at the wormhole's throat would necessitate robust engineering solutions. Communication between ends of a wormhole would be instantaneous, offering intriguing possibilities for real-time data transmission across vast distances. This could revolutionize communication and exploration. Wormhole engineering also raises philosophical and ethical questions. The ability to traverse great distances instantaneously would have profound implications for society, privacy, and security. Some theories suggest that wormholes could also connect different times, not just different locations. This raises the possibility of time travel, with all its associated paradoxes and ethical dilemmas. Current research in wormhole engineering is purely theoretical, but it pushes the boundaries of our understanding of space-time. Each new insight brings us closer to understanding whether wormholes could one day be a reality. International collaboration and interdisciplinary research will be crucial in advancing this field. Physicists, engineers, and material scientists must work together to tackle the immense challenges wormhole engineering presents. As we explore the potential of wormhole engineering, we push the limits of what is possible. The dream of instant travel across the cosmos continues to inspire and drive scientific innovation. Quantum computers represent a revolutionary leap in computing technology, harnessing the principles of quantum mechanics to process information in fundamentally new ways. Unlike classical computers, which use bits to represent data as zeros or ones, quantum computers use qubits that can represent both 0 and 1 simultaneously. This property, known as superposition, allows quantum computers to perform many calculations at once. The potential computational power of quantum computers far exceeds that of classical computers, enabling them to solve complex problems more efficiently. Another key principle of quantum computing is entanglement. When qubits become entangled, the state of one qubit is directly related to the state of another, no matter the distance between them. This interconnectedness can be used to perform highly complex computations and transfer information instantaneously. Quantum computers hold promise for advancing fields like cryptography, where they could break traditional encryption methods. They also have potential applications in drug discovery, material science, and optimizing large-scale systems. Developing practical quantum computers requires overcoming significant technical challenges. Qubits are highly sensitive to their environment, and maintaining their quantum state requires precise control and isolation. Quantum error correction is another critical area of research. Quantum computers need robust methods to detect and correct errors without disrupting the quantum state, a complex task given the fragile nature of qubits. Companies like IBM, Google, and Rigetti are making strides in quantum computing, building prototypes and demonstrating quantum supremacy. Quantum supremacy refers to a quantum computer performing a calculation that is practically impossible for classical computers. One of the most famous algorithms for quantum computers is Shor's algorithm, which can factor large numbers exponentially faster than the best-known algorithms for classical computers. This capability poses both opportunities and risks for cybersecurity. Quantum computers could also revolutionize artificial intelligence and machine learning. Their ability to process vast amounts of data simultaneously could significantly accelerate the training of complex models. Another exciting application is in the field of simulation. Quantum computers can simulate quantum systems naturally, making them ideal for studying molecular and atomic interactions in ways that classical computers cannot. Quantum computing is still in its infancy, and practical large-scale quantum computers are likely years away. However, the ongoing research and development in this field continue to push the boundaries of what is possible. The integration of quantum computers with classical computing systems is another area of exploration. Hybrid systems could leverage the strengths of both types of computers to tackle a broader range of problems. Quantum computing also raises important ethical and societal questions. The potential to disrupt industries, challenge current cryptographic standards, and impact global security needs to be carefully managed. Education and workforce development are crucial as the field of quantum computing grows. Preparing a new generation of scientists, engineers, and technologists with the skills needed to advance quantum computing is essential. International collaboration will play a vital role in the advancement of quantum computing. Sharing knowledge and resources across borders can accelerate progress and ensure the technology is developed responsibly. Quantum computers represent one of the most exciting frontiers in modern science and technology. Their potential to transform industries and solve some of the most complex problems humanity faces underscores the importance of continued investment and research in this groundbreaking field. Advanced propulsion systems are essential for the future of space exploration. They offer the potential to travel faster and farther than ever before, opening up new possibilities for human and robotic missions. One promising technology is ion propulsion, which uses electric fields to accelerate ions and create thrust. Ion engines are highly efficient, allowing spacecraft to carry less fuel and travel longer distances. Another cutting-edge propulsion method is nuclear thermal propulsion. This technology uses a nuclear reactor to heat a propellant, producing thrust with much higher efficiency than chemical rockets. Nuclear propulsion could significantly reduce travel time to distant destinations like Mars, making crewed missions more feasible. It provides higher thrust and efficiency, essential for deep space exploration. Solar sails represent another innovative approach to propulsion. These sails capture the momentum of photons from the sun, providing a continuous thrust without the need for fuel. The concept of laser propulsion involves using powerful ground-based lasers to propel spacecraft. This method could potentially achieve very high speeds, ideal for interstellar missions. Antimatter propulsion is one of the most speculative but exciting possibilities. Antimatter reactions release immense energy, which could propel spacecraft to near-light speeds. Developing practical antimatter propulsion faces significant challenges, including producing and storing sufficient amounts of antimatter safely. However, the potential benefits make it a compelling area of research. Another futuristic concept is the Alcubierre warp drive. This theoretical propulsion system involves creating a warp bubble around a spacecraft, allowing it to travel faster than light without violating the laws of physics. While the warp drive remains purely theoretical, studying such concepts pushes the boundaries of our understanding of physics and inspires innovative approaches to propulsion. Electric propulsion systems like the Hall thruster use magnetic fields to accelerate ions. These systems offer efficient, long-duration thrust, suitable for various space missions. Plasma propulsion, which uses ionized gas to generate thrust, is another advanced technology being explored. It combines high efficiency with the potential for high thrust levels. Fusion propulsion, harnessing the power of nuclear fusion reactions, promises immense energy output. If realized, it could enable rapid travel to distant planets and even other star systems. Solar electric propulsion combines solar power with electric propulsion methods, providing a sustainable and efficient means of travel within our solar system. It's particularly suitable for long-duration missions. Advanced propulsion systems are not just about speed and efficiency. They also offer the potential for safer and more sustainable space travel, reducing the risks and costs associated with long-duration missions. The development of these propulsion technologies requires international collaboration, significant investment, and innovative research. Their success will shape the future of space exploration, enabling humanity to reach new frontiers and explore the vastness of space. The limitations of current technology present significant challenges for realizing advanced concepts like time travel and near-light speed propulsion. Our existing propulsion systems are primarily chemical-based, offering limited efficiency and speed. Chemical rockets, while effective for reaching orbit and the moon, are not suitable for long-duration interstellar missions. They require massive amounts of fuel, making them impractical for distant space travel. Current spacecraft also face significant limitations in power generation and energy storage. Solar panels and batteries provide limited energy, insufficient for the demands of advanced propulsion systems like ion or nuclear engines. The development of reliable and powerful nuclear reactors for space use is still in its early stages. Technical, safety, and regulatory challenges need to be addressed before nuclear propulsion can become a reality. Ion propulsion, while efficient, produces relatively low thrust. This means it takes a long time to accelerate to high speeds, making it unsuitable for missions requiring quick travel. Radiation protection remains a critical challenge for long-duration space missions. Current shielding technology is inadequate to protect astronauts from the harmful effects of cosmic radiation and solar flares. The precision required for navigating and controlling spacecraft at high speeds is beyond our current capabilities. Small errors in trajectory could have catastrophic consequences for missions traveling at a significant fraction of light speed. Communication delays also pose a challenge for managing and coordinating deep space missions. As spacecraft travel farther from Earth, the time it takes for signals to travel back and forth increases significantly. Materials science is another area where current technology falls short. We need stronger, lighter, and more durable materials to withstand the stresses of high-speed space travel and the harsh conditions of space. The production and storage of antimatter, which could revolutionize propulsion, are not feasible with current technology. Antimatter is expensive and difficult to produce, and storing it safely is a significant hurdle. Quantum computers, which could help solve complex problems related to space travel and time travel, are still in their infancy. Practical, large-scale quantum computing is likely years or even decades away. The development of practical fusion reactors, which could provide immense energy for propulsion, remains an ongoing scientific challenge. Controlled nuclear fusion has yet to be achieved in a stable and sustained manner. Public and political support for ambitious space projects is also a limitation. Large-scale investments and international cooperation are crucial, but securing funding and agreement on priorities can be challenging. Robust and reliable life support systems are essential for long-duration human missions. Current technology needs significant advancements to ensure the safety and health of astronauts over extended periods in space. Addressing these technological limitations requires continued research, innovation, and collaboration across scientific disciplines. Overcoming these challenges will be essential for advancing our capabilities in space exploration and realizing the dreams of time travel and interstellar journeys. The Tipler cylinder is a hypothetical concept proposed by physicist Frank Tipler as a potential time machine. It involves a massive, infinitely long cylinder that rotates at high speeds. According to Tipler's theory, if the cylinder's rotation speed is fast enough, it could warp space-time in such a way that closed time-like curves are formed. These curves could theoretically allow for backward time travel. The concept is grounded in general relativity, which describes how massive objects can bend space-time. The extreme conditions around the rotating cylinder would create the necessary distortions in space-time. One of the main challenges of the Tipler cylinder is its requirement for an infinite length. This is physically impractical, as creating an infinitely long structure is beyond our current technological capabilities. Additionally, even if the cylinder could be of finite length, it would still need to be incredibly massive and rotate at near light speeds. Generating and sustaining such rotation would require enormous amounts of energy. The Tipler cylinder would also need to be constructed from materials that can withstand extreme stresses. Current materials science does not provide us with the needed strength and resilience for such a structure. Another issue is the potential for catastrophic consequences if anything goes wrong. The energy involved in maintaining the cylinder's rotation and stability could have unpredictable and possibly devastating effects. Despite these challenges, the Tipler cylinder remains an interesting theoretical model. It helps physicists explore the limits of general relativity and the conditions under which time travel might be possible. The Tipler cylinder also raises philosophical questions about the nature of time and causality. If backward time travel were possible, it would fundamentally alter our understanding of cause and effect. The concept has been explored in various science fiction stories, illustrating both the potential and the dangers of such a time machine. These narratives often highlight the ethical and practical dilemmas associated with manipulating time. While the Tipler cylinder remains purely theoretical, it continues to inspire research in theoretical physics. Studying such extreme models pushes the boundaries of our knowledge and helps refine our theories. Some physicists propose modifications to the original concept to make it more feasible. These include using advanced materials or alternative configurations to achieve the required space-time distortions. The study of the Tipler cylinder also intersects with other areas of physics, such as black holes and quantum mechanics. Insights gained from these fields could potentially inform the development of more practical time travel theories. Ultimately, while the Tipler cylinder may never be realized, its exploration enhances our understanding of the universe. It challenges us to think creatively and boldly about the possibilities of time travel and space-time manipulation. As we continue to investigate the theoretical underpinnings of time travel, concepts like the Tipler cylinder serve as valuable thought experiments. They encourage us to question the limits of physics and the potential for future technological breakthroughs. The Alcubierre warp drive is a theoretical concept proposed by physicist Miguel Alcubierre in 1994. It suggests a method for faster-than-light travel by warping space-time itself. According to Alcubierre's theory, a spacecraft could achieve faster-than-light travel by contracting space in front of it and expanding space behind it. This would create a warp bubble that moves the spacecraft along. The key idea is that the spacecraft would not move through space in the traditional sense. Instead, space itself would move, allowing the spacecraft to effectively travel faster than light without violating relativity. One of the main challenges of the Alcubierre warp drive is the requirement for exotic matter. This exotic matter would need to have negative energy density to create the warp bubble. Negative energy density is not something that has been observed in nature. Its theoretical existence is crucial for the stability of the warp bubble and the feasibility of the warp drive. Another significant challenge is the immense amount of energy required. Estimates suggest that creating and maintaining a warp bubble would require energy equivalent to that of an entire star. Theoretical physicists are exploring ways to reduce the energy requirements, Some proposals involve modifying the shape of the warp bubble or using different configurations to make the concept more feasible. If the Alcubierre warp drive could be realized, it would revolutionize space travel. Interstellar distances could be traversed in a matter of weeks or months, making exploration of other star systems possible within a human lifetime. The concept has captured the imagination of both scientists and science fiction writers. It is a popular topic in literature and media, often depicted as the key to unlocking the mysteries of the galaxy. Despite its theoretical appeal, the Alcubierre warp drive remains speculative. There are many unanswered questions and technical hurdles that need to be overcome before it can become a reality. The idea of manipulating space-time in such a dramatic way also raises questions about the potential impacts on the fabric of the universe. The creation of a warp bubble could have unforeseen consequences. Some researchers are studying the potential for using the Alcubierre warp drive for time travel. The manipulation of space-time could theoretically allow for backward and forward movement in time. International collaboration and interdisciplinary research are essential for advancing our understanding of the Alcubierre warp drive. Combining insights from physics, engineering, and cosmology could bring us closer to realizing this concept. While the Alcubierre warp drive is currently beyond our technological reach, it serves as an inspiring goal. It pushes scientists to think creatively about the possibilities of space travel and the manipulation of space-time. Exploring concepts like the Alcubierre warp drive helps expand the boundaries of our knowledge. It challenges us to question what is possible and to pursue innovative solutions to the fundamental challenges of space exploration. The Gott time machine is a theoretical concept proposed by physicist J. Richard Gott. It involves using cosmic strings to create closed time-like curves, potentially allowing for time travel. Cosmic strings are hypothetical one-dimensional defects in space-time, predicted by some models of the early universe. They are incredibly dense and have immense gravitational pull. Gott's idea is to use two cosmic strings moving past each other at high speeds. The interaction between their gravitational fields could warp space-time enough to create a loop, enabling time travel. One of the major challenges of the Gott time machine is the existence of cosmic strings themselves. While they are predicted by theory, no direct evidence for cosmic strings has been found. Even if cosmic strings do exist, controlling and maneuvering them would be an enormous technical challenge. The energy and precision required are far beyond our current technological capabilities. The Gott time machine also faces potential paradoxes, similar to other time travel concepts. The creation of closed time-like curves could lead to situations where causality is violated. Theoretical physicists have debated the feasibility of the Gott time machine. Some argue that the required conditions are too extreme to be practically achievable, while others explore modifications to make the concept more viable. Another issue is the stability of the closed time-like curves. Quantum effects might destabilize these curves, preventing the formation of a functional time machine. The study of the Gott time machine intersects with research on general relativity and quantum gravity. Understanding how these fields interact is crucial for determining the viability of any time travel mechanism. The Gott time machine also raises philosophical questions about the nature of time and causality. If time travel were possible, it would challenge our fundamental understanding of cause and effect. Despite its speculative nature, the Gott time machine stimulates valuable scientific discussion. It pushes researchers to explore the limits of our current theories and consider new possibilities. Cosmic strings themselves are a fascinating area of study. Whether or not they can be used for time travel, understanding these structures could provide important insights into the early universe and the nature of space-time. The concept has also found its way into science fiction, inspiring stories that explore the implications of time travel using cosmic strings. These narratives help popularize complex scientific ideas. As with other time travel theories, international collaboration is key to advancing our understanding. Combining expertise from various fields can help address the numerous challenges and questions posed by the Gott time machine. Exploring theoretical concepts like the Gott time machine encourages innovation and curiosity. It reminds us of the vast unknowns in our universe and the potential for groundbreaking discoveries in the future. Ronald Mallet, a theoretical physicist, proposed a time machine based on the concept of a rotating ring laser. His idea involves using a circulating beam of light to create a rotating region of spacetime. The rotating ring laser generates a powerful gravitational field. According to general relativity, this could twist spacetime in such a way that closed time-like curves are formed. Mallet's concept is inspired by the frame-dragging effect, where rotating massive objects can drag spacetime around with them. This effect has been observed around rotating black holes. The practical implementation of Mallet's idea involves building a device with a circulating laser beam. The beam would need to be intense enough to create a significant gravitational effect. One challenge of Mallet's rotating ring laser is the amount of energy required. The laser would need to operate at extremely high power levels to produce the necessary space-time distortion. Another issue is the stability of the closed time-like curves. Theoretical models need to ensure that these curves can exist without collapsing or causing destructive interference. Mallet has suggested that his concept could allow for limited time travel, possibly sending information or small particles backward in time. However, scaling this up to human time travel remains speculative. The rotating ring laser concept is still in the early stages of theoretical development. Experimental verification and refinement of the idea are necessary to assess its feasibility. Critics argue that the energy requirements and technical challenges make Mallet's proposal unlikely to be realized with current technology. However, it continues to inspire discussion and research. Mallet's work brings attention to the possibilities of using light and electromagnetic fields for time travel. It opens up new avenues for exploring the interaction between light, gravity, and space-time. The concept also highlights the importance of interdisciplinary research. Combining insights from optics, quantum mechanics, and general relativity is crucial for developing new theories and technologies. Mallet's rotating ring laser has captured public interest, partly due to his personal story and dedication to the idea. His efforts demonstrate the passion and persistence required to explore unconventional scientific ideas. Further research into Mallet's concept could lead to advancements in our understanding of space-time manipulation. Even if practical time travel remains elusive, the study could have other applications in physics and engineering. International collaboration and support for innovative research are essential. By fostering a global scientific community, we can better tackle the complex challenges posed by time travel theories. Mallet's rotating ring laser serves as a reminder of the imaginative and boundary-pushing nature of theoretical physics. It encourages us to think creatively about the possibilities of the universe and our place within it. Kip Thorne, a theoretical physicist, has significantly contributed to the study of wormholes. His work explores the possibility of using wormholes for time travel and faster-than-light travel. Thorne's wormholes are hypothetical tunnels in space-time that could connect distant points. These tunnels could potentially allow for instantaneous travel between distant locations. The concept of traversable wormholes was popularized by Thorne in the 1980s. He proposed that such wormholes could be stable and traversable if they were supported by exotic matter with negative energy density. Exotic matter is crucial for keeping the wormhole open and preventing it from collapsing. This type of matter has unusual properties, such as negative mass, which are not found in ordinary matter. One of the significant challenges in realizing Thorne's wormholes is the creation and stabilization of exotic matter. Currently, there is no known way to produce or maintain this exotic matter in sufficient quantities. Thorne's theoretical work has inspired both scientific research and science fiction. The concept of wormholes has been featured in numerous books and movies, capturing the imagination of the public. Thorne's work on wormholes also intersects with general relativity and quantum mechanics. Understanding how these theories interact is crucial for assessing the feasibility of wormholes as a means of travel. One potential application of Thorne's wormholes is time travel. If a wormhole connects two different times, traveling through it could theoretically allow someone to move backward or forward in time. The stability of a wormhole is another critical concern. Ensuring that a wormhole remains open and traversable without collapsing requires precise conditions and control over exotic matter. Thorne's ideas have prompted discussions about the nature of causality and the potential paradoxes of time travel. If wormholes allow for time travel, it raises questions about how events unfold and interact across time. Despite the speculative nature of wormholes, research in this area continues to push the boundaries of theoretical physics. Scientists explore various models and configurations to understand better the conditions under which wormholes might exist. Thorne's contributions extend beyond wormholes. He has also worked on the detection of gravitational waves and other phenomena related to the curvature of spacetime. His collaboration with other physicists and participation in interdisciplinary research highlight the importance of a collaborative approach to solving complex scientific problems. Thorne's wormholes remain a topic of intense interest and investigation. While practical implementation is currently beyond our reach, the theoretical exploration provides valuable insights into the nature of the universe. The study of Thorne's wormholes encourages us to think creatively about space, time, and the fundamental laws that govern our reality. It exemplifies the ongoing quest to understand and perhaps one day harness the deeper workings of the cosmos. The nature of time has been a subject of fascination and debate for centuries. Philosophers, scientists, and thinkers have all sought to understand what time is and how it shapes our reality. Time is often perceived as a linear progression, moving from past to present to future. This straightforward view underpins much of our daily experience and planning. However, theories in physics, particularly relativity, challenge this simple perspective. According to Einstein, time is relative and can vary depending on speed and gravity, intertwining with the fabric of space to form spacetime. The concept of spacetime suggests that time is not a constant universal flow, but rather a dimension that can be stretched and warped. This has profound implications for our understanding of the universe. Quantum mechanics further complicates the picture. It introduces the idea that particles can exist in multiple states simultaneously, leading to questions about whether time at the quantum level is fundamentally different from our macroscopic experience. Philosophically, time raises questions about existence and change. Ancient philosophers like Heraclitus believed that change is central to the nature of time, while Parmenides argued that reality is unchanging and time is an illusion. The arrow of time, a concept introduced by Arthur Eddington, describes the one-way direction of time from past to future. This concept is closely linked to the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time. Psychologically, time is experienced subjectively. Our perception of time can vary based on attention, emotions, and experiences. Moments of joy may feel fleeting, while periods of boredom can seem interminable. Cultural perspectives on time also differ. Some cultures view time as cyclical, with events repeating in a continuous loop, while others see it as linear, with a clear beginning and end. The nature of time also influences how we think about our lives and decisions. The idea of a finite amount of time can drive us to make meaningful choices and prioritize what matters most. Time travel theories challenge our understanding of time by suggesting it might be possible to move backward or forward through this dimension. These ideas force us to reconsider what time is and how it works. The concept of eternalism posits that past, present, and future all coexist simultaneously, challenging our perception of a flowing, dynamic present. This view aligns with some interpretations of relativity. Presentism, on the other hand, holds that only the present moment is real, and the past and future are mere abstractions. This view emphasizes the immediate experience of time. Scientific exploration into the nature of time continues to evolve. Advances in technology and theoretical physics might one day provide deeper insights into what time truly is and how it governs the universe. Understanding the nature of time is crucial for many fields, from physics to philosophy to cognitive science. It shapes our worldview, influences our decisions, and underpins the fundamental structure of reality. Free will versus determinism is a central debate in philosophy, addressing whether our actions are freely chosen or predetermined by prior events. This debate has profound implications for morality, responsibility, and human agency. Determinism is the idea that all events, including human actions, are determined by previous causes. If determinism is true, it suggests that every action we take is the result of preceding conditions and natural laws. In a deterministic universe, the future is fixed and inevitable. This view can be unsettling, as it implies that our sense of making choices is merely an illusion. Free will, on the other hand, is the belief that humans can make choices that are not predetermined. Advocates of free will argue that individuals have the power to influence their own actions and outcomes. The concept of free will supports notions of moral responsibility and accountability. If we can choose our actions, we can be held responsible for them, which is foundational to legal and ethical systems. Compatibilism attempts to reconcile free will and determinism. Compatibilists argue that free will is compatible with a deterministic universe, suggesting that we can still act freely within a framework of determined laws. Incompatibilists believe that free will and determinism cannot coexist. If our actions are determined, they argue, true free will cannot exist. Quantum mechanics introduces an element of randomness at the subatomic level, which some interpret as a potential space for free will. However, randomness alone does not guarantee meaningful choice. Philosophers like Immanuel Kant have argued for a form of free will that exists alongside deterministic natural laws. Kant suggested that while our physical actions might be determined, our moral choices stem from a different realm of reasoning. Neuroscience has added another layer to the debate, examining how brain activity relates to decision-making. Studies showing that brain activity precedes conscious decision-making challenge traditional notions of free will. Despite these challenges, the belief in free will persists in many cultures and philosophies. It is integral to our understanding of agency, creativity, and personal growth. The debate also intersects with religious views. Many religious traditions teach that humans have free will to choose their paths, while others emphasize divine predestination. Time travel narratives often explore the tension between free will and determinism. Characters may struggle with whether they can change the future, or if events are destined to unfold in a particular way. This debate impacts how we view ourselves and our place in the universe. It influences our understanding of autonomy, control, and the capacity for change. Ultimately, the question of free will versus determinism remains unresolved. It continues to provoke thought and discussion, challenging us to consider the nature of our choices and the forces that shape our lives. The concept of change is central to our understanding of time and existence. Change is the process through which something becomes different, transforming from one state to another. In philosophy, change raises fundamental questions about identity and continuity. How does something remain the same entity while undergoing change? Heraclitus famously said that you cannot step into the same river twice, emphasizing that change is constant and everything is in flux. This view highlights the dynamic nature of reality. In contrast, Parmenides argued that change is an illusion and that reality is unchanging. This perspective challenges our everyday experience of the world and raises questions about the nature of perception. Scientific theories often revolve around the concept of change. Evolution explains the change in species over time, while thermodynamics studies the changes in energy and entropy. Change can be gradual or sudden, affecting individuals, societies, and the universe itself. Understanding the mechanisms of change helps us navigate and adapt to our ever-evolving environment. In literature and storytelling, change is a key element of character development and plot progression. Characters grow, learn, and transform, reflecting the human experience of change. Change can be positive or negative, bringing growth and improvement or loss and decline. Our ability to manage and respond to change shapes our resilience and adaptability. Time travel narratives often explore the impact of change on timelines and histories. Altering a single event in the past can ripple through time, leading to significant and unexpected consequences. Technological advancements drive significant societal changes, influencing how we live, work, and interact. Understanding these changes helps us anticipate and prepare for future developments. Personal change involves growth and self-improvement, often driven by experiences and challenges. Reflecting on change helps us appreciate our journey and the lessons learned along the way. Cultural change occurs as societies evolve, adopting new customs, technologies, and ideas. This process can lead to progress, but also to conflicts and adjustments. Change is also a central theme in environmental science. Studying climate change, for example, involves understanding how human activities alter the planet's systems and how we can mitigate these effects. In the business world, change management is crucial for adapting to market shifts, technological advancements, and organizational growth. Effective change management strategies ensure that transitions are smooth and successful. Ultimately, the concept of change is intertwined with the passage of time. It shapes our understanding of history, progress, and the future, reminding us that nothing remains static and that adaptation is key to survival and growth. Human perception of reality is a complex and multifaceted phenomenon. It involves how we interpret and make sense of the world around us through our senses and cognitive processes. Our perception is influenced by sensory inputs, including sight, sound, touch, taste, and smell. These inputs are processed by our brains to create a coherent picture of reality. Cognitive processes such as attention, memory, and interpretation play significant roles in shaping our perception. They help us focus on relevant details and integrate new information with existing knowledge. Perception is not a perfect reflection of reality. It is subject to biases, illusions, and limitations inherent in our sensory systems and cognitive processes. For example, optical illusions can trick our brains into seeing things that are not there. These illusions reveal how our visual system interprets and sometimes misinterprets sensory information. Cultural and social factors also shape our perception of reality. Our beliefs, experiences, and social context influence how we interpret and understand the world. Perception is dynamic and can change over time. As we gain new experiences and information, our understanding and interpretation of reality can evolve. The concept of reality itself can vary between individuals and cultures. Different people might perceive and interpret the same event in diverse ways based on their backgrounds and perspectives. Philosophers have long debated the nature of reality and perception. Some argue that reality is independent of our perceptions, while others believe that our perceptions shape and construct our reality. Technological advancements, such as virtual reality, challenge our traditional understanding of perception. They create immersive experiences that blur the lines between the physical and digital worlds. Perception is also a key topic in psychology. Understanding how people perceive and process information can help in addressing mental health issues and improving communication and learning. In the realm of art and literature, perception is often explored through different perspectives and interpretations. Artists and writers play with perception to evoke emotions and provoke thought. The study of perception extends to artificial intelligence and machine learning. Developing systems that can perceive and interpret their environment is a significant challenge in creating autonomous machines. Perception plays a crucial role in our interactions and relationships. Misunderstandings often arise from differences in how we perceive and interpret situations and intentions. Ultimately, perception is a fundamental aspect of the human experience. It shapes our reality, influences our actions and decisions, and connects us to the world and each other in profound ways. We've journeyed through a fascinating exploration of time travel, examining both the scientific and theoretical frameworks that underpin this intriguing concept. From Einstein's theories of relativity to the speculative nature of wormholes and cosmic strings, we've covered a range of topics that challenge our understanding of time and space. We've delved into the paradoxes that time travel might introduce, like the grandfather paradox and the bootstrap paradox, highlighting the complexities and philosophical questions they pose. The discussions on closed time-like curves and the impact of quantum mechanics have offered deeper insights into how time travel could theoretically work. Our exploration extended to modern theoretical proposals such as the Tipler cylinder and the Alcubierre warp drive, which provide intriguing possibilities for future advancements. We've also considered the implications of such technologies and their portrayal in popular culture, showing how science fiction has shaped our perceptions of time travel. Through a look at advanced propulsion systems and high-energy particle accelerators, we've seen how ongoing research could pave the way for practical applications of time travel. The potential breakthroughs and interdisciplinary collaborations hint at a future where these concepts could move from theory to reality. As we wrap up this comprehensive overview, I hope you found the journey through time travel theories and technologies as captivating as I have. If you enjoyed this video, please take a moment to like and subscribe to our channel. Your support helps us continue exploring these incredible topics and sharing them with you. Be sure to check out the rest of the videos on our channel for more in-depth discussions and analyses of groundbreaking scientific concepts. Each video is designed to provide you with valuable insights and updates on the latest developments in science and technology. If you have any questions or comments about time travel or other fascinating subjects, feel free to leave them below. Your feedback helps us improve and tailor our content to better suit your interests. Thank you for joining us on this journey through the mysteries of time travel. Stay tuned for more exciting content as we continue to explore the frontiers of science and technology together. Remember, every discovery begins with curiosity and a desire to learn. Keep exploring, keep questioning, and we look forward to sharing more groundbreaking content with you soon. Until next time, keep imagining the possibilities and pushing the boundaries of what we know about the universe.